Hey, welcome guys. Yeah, so today we finished the integral, right? So let's talk about the sequence and the series of functions. So basically this is follow the routine chapter 7. Yeah, so after we've so usually I think the advanced analysis start from the basic topology and go to the continuous and then go to the differential and then go to integral. So you can view this is the half finish the calculus part, right? So start from now, we are talking about something which calculus will not touch, basically sequence and a series of functions. Yeah, this is very interesting topic. Uniform convergence will blow my mind when I was undergraduate. Okay, yeah. So basically this follows the routine, and our key idea is to understand the limit and the integration and the differential with respect to some sequence of functions. Okay, so I hope you guys subscribe to my channel, and you can see my previous advanced mathematics list in my video. Okay. Okay, so we know that let's say given a definition. So this is okay. So suppose f of n, which is let's say from 1 to 2 to 3, is a sequence of function defined on E, right? So basically you have a sequence of function, and then let's say suppose, so you can pick up some x, right? You can fix some x in E, and the f of n of x will give you a series, right? Will give you giving you a sequence of number, so it's also a sequence. Okay, so if this converge, if for each x, this f of n of x converge, right? So converge to f, then we say fn converge to f. Okay, so you fix x, and you can find f of x, right? So f of x is that means that for each x, these my assumption is that these sequence converge, right? So for each x, so I can define the f to be convergence results. Okay, so yeah, so this is called a limit function. Or basically, sometimes we say that f n converge pointwisely. So converges pointwisely. Since for each point it converge, right? So pointwise on E. Okay. Okay. Now, you can also define if you can also define this, right? So for each, if you have for each x and the sum of fn of x from n from infinity, these guy converge. Then you can also define a converge of the summation, right? So basically sum of the series. Okay. So the key problem is that the key problem. Okay, so there are many key problems. Okay, so the first key problem is that yeah. So basically, the first key problem is that suppose that you that t goes to x and n goes to infinity f of n. This may not exist. And this may not the same as limit n goes to infinity or limit t goes to x fn of t. So basically, this is very very frustrated because if you do a change of the limit, one is the discrete, one is continuous. This will fail. Okay, so will fail. And more generally, there's a so-called double sequence. So double sequence will blow your mind, right? So m goes to infinity, n goes to infinity. You define f of n m, right? So even though for each one it converge, these two may not be the same. Okay, so let's give a simple example. Let's say Smn is to be m plus divided by n, and m came from 1 to 2 to infinity, and n from 1 to 2 to infinity. Okay, so let's see. So obviously that for fixed n, right? So once I fix n, right, I fix n, and I let m go infinity, right? So I guess that you guys is very smart, right? So fix n, m goes to infinity will give you what? Will give you what? Okay. Okay, so since for each m is 1, right? So that means if you go to n to infinity and then go to m to infinity, then this smn will goes to 1. By the way, sometimes I write this limit, sometimes I write this limit. So just my bad notation right here. Okay. However, if you fix, okay, so this is if you fix, let's say we fix m. So if I fix m and that n goes to infinity, then this guy becomes 0, right? So which tells me that this will become 0, right? So this is not the same as this. Okay, so this is called a double sequence. Okay, so which is very frustrating. Okay, so this is the fail example number 1. Okay, so that means these will fail. These will generally fail. Okay, how about this? Okay, so let's see. This x actually will still fail. Okay, so let me just take this example. So that f of n of x, x squared plus 1 is x squared n, right? And n is 0, 1 to 2. Okay, so let's consider a summation. Okay, so this is summation, right? So so obviously that f of n 0 will be 0, right? For each n, right? So that means f of 0 will be 0, right? Okay, obviously. But let's see if x is non-zero. What is the case if x is non-zero, right? So if x is non-zero, then these guys are what? Geometrical series, right? So this is x squared. Now 1 minus the ratio, right? I guess is this. Okay. So the answer will be 1 plus x squared, right? So that means your final f of x is actually, if x is 0, then it becomes 0. If x is non-zero, this is 1 plus x squared, right? So you can see that when x approaches 0, this is 1, this is 0, right? So f of x is not continuous. Okay, so that means we have some behavior, very weird behavior, that each f of n is continuous. And then f of n converge pointwisely. So in this case, summation, right? But it's fine that in this case, summation. So it's if summation converge pointwisely, but then f can be discontinuous. Okay, so this is the second issue. Okay, so let's see another example, which is also will make you crazy. Okay. Okay, so limit mathematics is so weird that once you involve the limit of something, which there are, so in the calculus, there are a lot of things will blow out your mind. Yeah, so let's consider this function. So which for let's see. So let's say this is m, that it is right. So for each m, so for each, let's say m is from 1 to 2 to 3, keep going. I define f of m to be n goes to infinity cosine m factorial pi x 2 to n. Okay. Okay, so let's see. So if so obviously that when m factorial times x is an integer, right? So suppose this guy is an integer, then this is the cosine, right? So cosine integer will be plus or minus 1, right? But you square 2n. So f of this guy, this x will give you 1. Okay. But for other o, right? For other o, it becomes 0, right? Because it will go to the 2n, right? So if x is not like this, so else your f of x will become 0, right? Because your power can be arbitrarily large. Okay, so which means that your f of m right, so for other values it becomes 0. Okay, so let's see, let f of x to be limit m goes to infinity, f of mx. Okay, so this function looks more weird, very weird. Okay, the reason is that let's say if x is irrational, right? So sorry, if x is irrational, that means what? That means m factorial times x is never be integer, right? Never be integer. So that means what? That means this guy is 0, right? So f of x must be 0. Because for each m, it must be 0, right? Okay, but the case is that what about let's see, right? So let's say if x belongs to rational, then let's say x is p over q, right? And obviously we ask about m factorial times x, right? So m factorial x will be integer if m greater than q, right? Or greater or equal to q. So that means for each, that means f of m of x is 1 for large enough, right? So which means that f of x can be 1. So combine these two discussion, I know that f of x is 1 if x is rational. Okay. Yeah, so that means the result will be what? Discontinuous, right? But this guy is continuous. So that means if your function converges pointwisely and then all of its functions continuous, it do not mean anything. Okay. Okay, so now let's working on some differential. Okay, so the problem look like this, right? So we know that if fn converges f pointwisely, then the f may not be continuous. Okay, so that means that even fn can be differentiable, right? It does not mean f can be, right? Because f may not be continuous. Okay, but if you make an assumption that f can do the differentiable, then it did not mean that their differential will be the same. Okay, so the question is that if you do the limit on each function, let's say this, right? And then you believe that this should be what? Should be the same, right? Should be the same as f of x. Let's say you fix some points, and there should be this, right? So basically, so one can view this equation like this, right? Okay, so the question is that where this can be can always valid, and the answer is I guess everyone knows the answer, right? And there is false. The counterexample can be easily found. So let's say f of n of x is sine n of x divided by square root of n. And the x is real, and the n can be 1 to infinity. Okay, so let's do the differential for x, right? So you get square n cosine nx. Right, so obviously that when n goes to infinity, this guy do not survive, right? This guy do not exist. So the left-hand side does not exist. Because your n goes to infinity, unless your x is some particular point, which this cosine is always 0. Okay, but how about f, right? So you see when n goes to infinity, then this guy becomes 0, right? Because this f of n is bounded by 1 over square root of n, so your f is 0. Okay, so that means its differential is 0, right? So 1 does not exist, 1 is 0, so very frustrating. Okay, next we talk about integral. Okay, so what you hope is that okay, so let's say f n of x is integrable maybe on a b, and then you hope that sure, if I go n goes to infinity, then hopefully it become this, right? Okay, so the answer is no. Okay, so let's do this let's say do this example. This example is famous, f of n of x will be n squared x 1 minus x squared n. Okay, obviously that let's consider this. Okay, so obviously that when x is 0, then it's 0, right? If x is 1, it's 0, and if x is anywhere between then, right? And then you can show that this is power law, right? So n squared is less than power law. So you can easily prove this by your simple calculus. Then this function is 0. Okay, so f is 0. Okay, and yeah, f is 0, right? So So this integral, if a b choose to 0, 1, then it must be 0, right? Because 0, so 0 integral 0. But how about this? How about n squared x 1 minus x squared n do a dx 0, 1? Okay, so a very easy exercise for you is to check this guy integral will be 1 over 2n plus 2. So this is n squared 2n plus 2. Okay. So if limit n goes to infinity, then this guy blows off. Okay. Okay, and if you choose n, okay, so if you define this to be n, then this is 1 over half, right? So however, right, this can be infinity, this can be 0, this can be finite, this can be 0. Okay. Oh, still frustrated. Okay, so that means we have many questions need to solve. Then we just outline them and we solve in the next time. And that's so that we can define a so-called uniform convergence to solve all these problems. Okay, so the first one is the double series. Okay. So that means if you go to different limit, then this can may not be the same. Okay. And the second is the continuous, right? So if each of f is conti, then convert pointwise to f, then f may not be conti. Okay, and the third example, the third property, so third problem is that the differential, right? The differential. So that means if you go to prime and do the limit, may not exist, may not the same as right? If you go and goes to infinity and you do prime, so it's f prime. Okay, and the third part is the first part is the integral, right? So the integral part is also tricky. So this guy goes to infinity may not be the same as this guy. Okay, so let me just write down a solution. The solution, okay, at least a part of the solution is that the partial solution is the idea of so-called uniform convergence. Okay, so that's why people care about uniform convergence, uniform equicontinuous or other uniformly bounded. Yeah, so usually if you're talking about a series sequence of functions, right, then you will always see something like uniform convergence, also uniform convergence and the uniform bounded, or there's a idea called equicontinuous. And then start from there, here you can define a more, you can prove more difficult theorem like stone wire truss. And many other different, more advanced ideas. So start from here, and then we bypass the calculus into more exotic area. Okay, see you guys next videos. Oh, by the way, subscribe to my channel. Thanks.